Depending on the composition C sub 0, several different types of microstructures are possible for the slow cooling of alloys belonging to the binary eutectic systems. After learning this lecture, you should be able to calculate the phase amounts and compositions for each phase for any given point on a eutectic phase diagram, and also be able to sketch the likely microstructures of a eutectic system given the composition and cooling treatment history. Sometimes we use a term microconstituent to describe the microstructures of a given eutectic system at a given composition. So microconstituent is a phase or a mixture of phases, if we have more than one phases, with a very characteristic appearance. So it can be one phase or a mixture of phases. It's the current appearance of the microstructure. We call it the microconstituent. We're going to use this lead and tin binary eutectic phase diagram to describe the development of the microstructures in a eutectic system. All other binary eutectic systems will behave the same way as this lead and tin phase diagram. So the first case of the microstructure is for the overall composition between a pure component and the maximum solubility at room temperature. So in the lead and tin system, if we check the room temperature line here, the maximum solubility for tin to be dissolved in lead is 2%. So at room temperature, we can only add 2% of tin into lead to form a single solid solution, right? So that's the solubility 2%. Now we're going to focus the composition between the pure lead and 2% of tin, this region, okay? And let's say we have a composition of C sub 0 that is below 2% of tin, and we're going to cool it down from above the liquidus temperature. Let's say this temperature is about 350. And then we cool it down, follow this dashed line. So at 350, we have a complete liquid because we are now in the liquid region. So the liquid has a composition of C sub 0. And that's the same composition as the overall composition. So as we cool it down, it will remain as liquid all the way until we reach this liquidus line. And starting from this liquidus line, the solid alpha phase begin to form. And within this very narrow region, we will have two phases, which is liquid plus solid. When we are within this liquid plus solid or liquid plus alpha region, right? We have two phases, liquid plus alpha. And with continuous cooling, more of the solid alpha forms and we have less liquid left. And furthermore, this liquid and solid phase compositions are different because the composition of the liquid phase will follow this liquidus line, and the composition of the solid phase will follow this solidus line. So these are two different lines, therefore the compositions will be different. Since this region is very narrow, so it's hard for us to see the composition, but think about if you draw a tie line, right? We figure out or we find the composition of each phase by using this tie line. We draw a tie line pass through this component point or composition point C sub 0. Now this point, the left intersection corresponds to the C alpha. That's the alpha composition. And this on the right, this composition or the intercept between the tie line and the liquid phase, right, it's the composition of the liquid phase. So that's why we say the composition of the liquid and solid phase are different. They will follow the liquidus line and solidus line respectively. As we cool down continuously, the solidification reaches completion at this point. The dashed line, the intersection of the dashed line with the alpha phase. So at this point, the last drop of liquid will be solidified into solid. So we only have solid alpha phase below this point. And the resulting alloy is polycrystalline with a uniform composition of C sub 0. And it's only one phase, which is the alpha phase, and there is no subsequent changes occur upon cooling to room temperature from this point. So again, for a composition of less than 2%, which is the solubility of tin in lead at room temperature, the result is polycrystalline with grains of alpha phase. It's a single alpha phase which have the composition of C sub 0 with the same composition or same overall composition. So for alloys with this microconstituent, it's solid solution alloys because we do not have a second phase. We only have one single phase. So solid solution alloys can be strengthened by strain hardening and grain size reduction, and also because we only have one solid solution, so it can be strengthened by solid solution strengthening. Next composition region we're going to look at is between 2% and 18.3% of tin. So the 2% is the solubility limit at room temperature, and 18.3% is the solubility limit of tin in lead at eutectic temperature at this point. And now if you still remember this line, we call this line the Solves line. So this is the solubility limit of tin in solid lead at any temperature. So any alloy containing between the 2% and 18.3% cools past this Solves line, the solubility limit is exceeded and a small amount of beta phase will form. So now let's take a look at this example. C sub 0 is between 2 and 18.3%, and we're going to examine the microstructure developments when we cool it down from above the liquidus temperature. So at beginning, again, we just have liquid phase, which has the overall composition C sub 0. And then we continuously cool it down. It will be liquid until it reaches this liquidus line. At this point, the alpha phase starts to form from the liquid phase. And within this region, the liquid plus alpha phase region, we will always have two phases, which is the liquid plus alpha. So again, if we use this one now as an example, it's more clear to see. Now, at this point, if we draw a tie line, the composition of the alpha phase is this point. If we read off from the composition axis, so C sub alpha. Now the alpha phase has about 10% of tin in it, 90% of lead in it. Now the liquid phase, the composition is read out from the other side of the tie line, which is about, let's say it's 24% of tin, and then the rest will be with lead. So we say that the liquid phase and solid phase has different compositions, and as we move down, cool it down following this dashed line, we need to draw different tie lines, and we can see that the solid phase composition changes along this solidus line, whereas the liquid phase composition will be for there, right? Changes along the liquidus line. So they are always different. So that's the driven force for diffusion. So the tin and lead will diffuse from one phase to another because of this composition difference. Now, if we cool down to this point, the intercept of the dashed line with the solidus line, so the last drop of liquid will be solidified into solid. So between this region, we will only have solid alpha because now this point is within the alpha phase region. It's a single alpha phase between this temperature region. And this solid alpha, single alpha phase has the same composition as the overall composition, C sub 0. And now, when we reach this Solvus line, let me write that down again. So this is the Solvus line. When we reach this line, that means the solubility exceeds the solubility of the tin in lead at the temperatures below this temperature, which is about, let's say that's 180, right? Below this 180, the lead cannot dissolve all of the tin, so there will be beta phase start to precipitate out from the alpha phase. So now we can see the microconstituents includes it consists of alpha phase, which is the first formed alpha phase, and then the latter formed beta phase. The red phases are beta phase, which is the precipitates from the original alpha phase. So the results at room temperature in the alpha plus beta region, we have two phases now, which are alpha and beta. And alpha phase is the polycrystalline alpha grains, and the beta phase is small particles. And this beta phase is called the precipitate phase. So some precipitation strengthening occurs as the beta solid precipitates. So that's another strengthening mechanism in addition to solid solution, grain size reduction, and string hardening. So this is called precipitation strengthening. The material is strengthened by a second phase, which precipitates from the primary phase. Beta phase is the precipitation, and alpha phase is strengthened by this beta phase. Now let's take a look at the alloy that has the eutectic composition, which is described by this eutectic point on the binary eutectic system. So for this lead and tin system, the eutectic composition is 61.9% of tin. This is the eutectic composition. So we said an alloy with the eutectic composition has the lowest melting temperature. And also this eutectic alloy melt or solidifies at one single temperature, which is this eutectic temperature, which is 183 degrees Celsius. So which means during the melting process or during the solidification process, no matter how long it takes, the temperature is a constant. It maintains at 183 degrees Celsius. But for other alloys, if you take a look, right, the melting process or the solidification process will be over a range of temperatures. So temperatures varies during the process. But for eutectic, the temperature is a constant temperature. So now let's take a look at this alloy with this eutectic composition. First, above this eutectic temperature, we have liquid phase only, which has a composition of 61.9%. And as we lower down the temperature following this dashed line, when we are at this eutectic point, not that yet. So at this eutectic point, we know there will be a reaction. So this liquid phase will form into two solid phases. So the eutectic reaction is written as the liquid phase, which has 61.9% of tin, will solidify or react into two phases. One is the alpha phase, one is the beta phase. Okay, based on this horizontal line, right? The top one above this point is liquid phase. On two ends, we have alpha and beta respectively. So the alpha phase will have the specific composition, which is the composition of, well, if you draw this read of the composition point here, it's about 19 or 18.3% of tin. So that's the composition of the alpha phase. It's always this value, okay, for the lead and tin eutectic system. And for the beta, it's about, again, that's the x-axis of this point, which is about 97.5. Depends on different resources. This value may be a slightly different value, okay? And this happens at temperature 183 degrees Celsius. So right after the complication of this reaction, we will have the microconstituent, which are two phases, alpha and beta. Again, right below the eutectic reaction, after it's completed, we have all the liquid are transformed into alpha and beta. So the composition of the alpha phase is 18.3 and the composition of beta phase is 97.8 based on this given phase diagram. Okay, let's change that to 8. All right. So again, two solid solutions, alpha and beta, are formed during the eutectic reaction. So now, as atoms are distributed during the eutectic solidification, a characteristic microstructure develops. So you see we have this kind of plate-like arrangement. We have layers of alternative layers of alpha and beta phase formed in the microstructure. So this is called the lamellar or lamellar structure, alternating layers of alpha and beta phases. So this lamellar structure permits the lead and tin atoms to move through the liquid in which diffusion is rapid without having to move a bigger amount of distance. So with this layered structure, the lead and tin atoms are easier to move into their corresponding phases because we can see that alpha phase is primarily the lead had only 18.3% of tin in it, but for beta phase it's primarily the tin with a little bit lead. So alpha is kind of a lead solution, solid solution of lead with tin, but beta phase is the solid solution of tin with lead. So this is the micrograph of the lead and tin eutectic microstructure. Again, you can see those layers. So this lamellae structure is a characteristic of numerous other eutectic systems. A lot of the eutectic systems have this lamellae structure or microconstituent. This figure shows the atom redistribution during the lamellae growth growth of the lead and tin eutectic structure. So we have solid formed into the liquid and gradually grow into the liquid, follow this direction, since this is the liquid portion. And we know alpha phase is the solid solution of lead with some tin inside, and beta phase is the solid solution of tin with some lead inside. So the tin atoms from the liquid prefers to dissolve into the beta plates, and the lead atoms diffuse into the alpha plates. So this layered structure or alternating layers of the structure will ease the movement of the corresponding atoms into their corresponding phases. Based on the relation between the composition and the eutectic composition, alloys can be classified as the hypoeutectic alloy and hypereutectic alloy. So the hypoeutectic alloy has a composition between the left endpoint over here of this eutectic reaction line and the eutectic composition. So the composition in this case for the lead and tin system is between 18.3, this point, and 61.9% of tin. If an alloy has a composition between this region, is the hypoeutectic alloy. And to the right, if the composition is between the eutectic composition and the right end of this tie line or the eutectic reaction line, this alloy is the hypereutectic alloy. So we know that for the eutectic alloy, it has the characteristic of the lamellae microconstituent, right? The layered alternating layers of alpha and beta phase. Now for the hypoeutectic, we have a primary alpha phase. So if we're going to explain it in more details later. But the microconstituent consists of a primary alpha phase. So if we use this one composition as an example, we see that from liquid phase, first we will have the alpha phase formed inside the liquid phase before we reach this eutectic reaction. So at this eutectic reaction, right above this eutectic reaction line, we have the alpha phase, which has a composition of 18.3% of tin, and we have this liquid phase, which has the eutectic composition, which is 61.9%. And now, right at this temperature, eutectic temperature, the remaining liquid will form or will start the reaction, the eutectic reaction, and liquid will form this eutectic composition of alpha plus beta. But the primary alpha stays the way it is. It doesn't participate in the reaction. Again, the reaction is only a reaction of liquid to form two solid phases. It is not from the alpha phase, right? Alpha phase doesn't participate in the reaction. Therefore, the final microstructure or microconstituents looks like this. We have the primary alpha phases, which is formed directly from the liquid above the eutectic reaction temperature. And the rest of it are the eutectic microconstituent, the lamellae structure, which is formed from the remaining liquid. And the remaining liquid has the eutectic reaction and formed this eutectic microconstituent. And same idea for the hypereutectic alloy. So from this cooling history, we know that from liquid we will first have primary beta phase formed, And then at the eutectic reaction temperature or eutectic temperature, we already have the primary beta phase. Let me draw it separately. We already have this primary beta phase and liquid remains, right? Remaining liquid. And this remaining liquid again has the composition, the eutectic composition. So we will start the eutectic reaction. So this remaining liquid will form the eutectic microconstituent. So the liquid will form into alpha plus beta, which again has its invariant point, which means the alpha must have this 18.3% of tin and beta must have 97.8% of tin. So the resultant microconstituent will be the primary beta phase, which is formed before the eutectic reaction, and the eutectic microconstituent. So here's one example of microstructural development in the hypoeutectic alloy, which has a composition between, or on this phase diagram example, I have 19% instead of 18.3. Again, it varies a little bit, but not a big deal. So if we just use 19% as given in this phase diagram, and the eutectic composition is 61.9%. So between this region, we have hypoeutectic. So at the beginning, if we cool down from the liquid phase, above this liquid line, we know we will have only liquid. So all of that will be liquid. And this overall composition is C0, it's 30%. So liquid now has a composition of 30%. When we continuously cool it down, right at this point, right, the liquidus line, when we heat this liquidus line, the alpha phase start to form in the liquid alpha phase. And as we continuously cool it down, but still within this alpha plus liquid region, the alpha phase will grow bigger, will occupy more liquid, right? More solid will form into the liquid or will consume the liquid. And composition of the liquid phase follows the liquidus line. Composition of the alpha phase follow the alpha line or the solidus line. And right above this point, okay, right above the eutectic composition line, or right above the eutectic temperature, if we draw a tie line, at this point, all this will have the solid alpha formed, which has this composition, which is 19% of tin. So that's the primary alpha. The rest of it will be liquid. Okay, so again, at this point, right above, just a tiny bit, very close to the eutectic reaction, but not yet. So reaction not happening yet at that temperature. Let's draw it similar to the one we have right there. So we have this primary alpha, and the rest of it will be liquid. So this liquid phase now is very close to the eutectic composition. Well, it's approximately the eutectic composition, and the alpha phase has the 19% of tin. And now at this eutectic temperature, the eutectic reactions start to happen. So the liquid with the eutectic composition will start to transform into the alpha and beta, the layer or lamellae structure, because of this eutectic reaction. Alpha. So now this alpha again has 19%, and beta phase has, well, when we check the reaction, you want to draw the timeline all the way to the beta phase. Okay, so alpha phase is still 19%, and beta phase is now 97.8%. But the primary alpha phase doesn't change. So from this step here, to a lower temperature, when you compare the two microstructures, the primary alpha phase doesn't change. Still those three parts, right, illustrated here, and the liquid phase will transform completely into alpha and beta composition. So this eutectic composition of alpha and beta is only valid for the temperature right below. Right below. Again, very close to the eutectic temperature. Right below this. Okay, it has the eutectic composition. But when we lower down the temperature, the alpha phase composition will change along this solvent line, and beta phase composition will change along the solvent line over there. In other words, if we draw a tie line here, and at this given temperature, about 80 degrees Celsius or 75 degrees Celsius, at this temperature, the alpha composition will no longer be 19%. It's about, if this is 10, this will be 5%, right? And beta phase is also a little bit lower than the 97.5%. So the composition changes with those boundary lines. Now we know that for the hypoeutectic alloy, which has a composition between the left point and the eutectic composition, for lead and tin system is 18.3% to 61.9% of tin. The resultant composition or microconstituent at room temperature will be the primary alpha phase particle and a eutectic microconstituent beta, alpha plus beta. So now let's do one example to find the phase compositions and phase amounts for a lead and tin alloy with a composition of 40% of tin. So during the cooling process, the development or the change of the phase compositions and amounts. So first of all, at room or at liquid phase, the liquid phase has a composition of 40% of tin. And when we cool it down to the liquidus temperature, now the alpha phase starts to form. So the first formed alpha phase has a composition of, if we're looking for that, then we just need to draw a tie line, pass through this point. And this is the alpha composition, which is about 18%, right? So the first formed alpha has 18% of tin. All right, again, use the tie line to figure that out. And now we cool it all the way down to right above the eutectic temperature. So assume this tie line is very close to the eutectic temperature, right above the eutectic temperature. And now the alpha composition is, we just used this point, the left end of the eutectic line, which is 18.3%. And the liquid composition is the eutectic composition. So again, your tie line will just stop at the boundaries of this region. So this is the alpha plus liquid region. So the tie line stops at the alpha phase and liquid phase respectively. So do not extend your tie line all the way to the beta, because that's not the boundary of this current region. So now we can calculate the phases present at this temperature right above the eutectic temperature. We have alpha phase plus liquid phase. So the alpha composition is 18.3 and the liquid composition is the eutectic composition 61.9%. Now the phase amount or the weight percentage of each phase, use the lever rule, we're going to figure that out, right? The weight percent of, or the phase amount of the alpha phase is the opposite lever S over the total length of the lever, R plus S. So the result will be 50% or 0.5. Again, this S equals to, just as a review, the S is CL minus C0. Let's replace it a little bit. So CL minus C0 is the S, and alpha plus, or R plus S, the entire lever length will be CL minus, this is the CL, this is C alpha, minus C alpha. All right, and the liquid phase will be the remaining, which is 1 minus the alpha phase. This is right above the eutectic reaction. And now, at the eutectic temperature, all of the alpha phase, or all of the liquid phase will be converted, or will transform into the alpha plus beta phase. And now let's take a look at right below the eutectic temperature, what happens. So right below that temperature, the alpha phase still remains as alpha, which again means we still have half of it as the alpha phase, 50% of alpha phase, and 50% of now is no longer liquid phase, but it will be alpha plus beta, or the eutectic alpha plus eutectic beta. To figure out this compositions and phase amounts and phase compositions, we need a new tie line this time. So this new tie line, again, is passed through the point here, right below the eutectic temperature, and extend all the way from the alpha to the beta. Okay, alpha to the beta, because now this point is within alpha plus beta region. So the two boundaries are alpha and beta respectively. So the tie line is here, and now the corresponding alpha phase still is the 18.3. We use this endpoint. For beta phase, it's the 97.8. So now the composition, just below the eutectic temperature, the composition of alpha phase is the same, 18.3. The composition of beta phase is 97.8. And the weight percent or phase amount of alpha is the same as, or is not the same, it's still the S, the right portion of the lever, but now it's longer. Okay, the line in red versus the previous one is the line in green. Okay, so now this new S is the new C sub beta minus C sub 0. So this is C sub 0, 97.8. Okay, so this S equals to C sub beta minus C sub 0. Okay, this is the C sub 0. It has nothing to do with the eutectic point anymore. We're done with that part. And the overall lever will be C sub beta minus C sub alpha. So the weight percentage or the phase amount for alpha phase is 0.73 or 73%, and the rest of it will be the beta phase. And by the way, this alpha phase, okay, alpha phase has two parts. One is the primary alpha, one is the eutectic alpha. So that's the overall alpha, including the primary alpha and the eutectic alpha. And both alpha has the same composition, which is 18.3. But one is formed from the initial liquid and one is formed from the eutectic liquid. As a summary, for eutectic phase diagrams, we have solid solution alloys. So for the lead and tin phase diagram, for example, we have alpha solid solution, which only has a single alpha phase, or beta solid solution, which only have a single beta phase. So for alpha single phase solid solution, it contains less than 2% of tin. For beta single phase solid solution, if you check the phase diagram, it's the beta phase which has the maximum solubility of 97.8% of tin, which means actually we have a beta phase which is rich in tin, and the component or the lead composition should be less than 2% of lead in it, okay, which is on the right end of the phase diagram. And solid solution alloys can be strengthened by solid solution strengthening. For alloys exceeding the solid solubility limit, which for alloys between 2% and 19% of the tin composition, also produces a single phase solid solution at the beginning before the eutectic temperature. But after the eutectic temperature, our second phase will precipitate out of the first one. Next, while we increase the tin composition, we will have a eutectic alloy. So the eutectic alloy has a fixed composition, which is exactly 61.9% of tin. And this composition has the lowest melting temperature, and this melting temperature is a constant value when solidification happens or when melting happens. So this is not a region of temperatures, but a single temperature. For eutectic composition, the microconstituent is lamellae structure microconstituent, which is the plate-like alternating layers of alpha and beta phase. So for hypo and hyper eutectic alloys, one is to the left of the eutectic composition, one is to the right of the eutectic composition. So we'll just use the hypo eutectic alloy as an example to explain the microstructural development of the alloy, but the hyper eutectic is similar, just that it's the primary phase is the beta phase instead of alpha phase. So the hypo eutectic alloys are between the left end of the eutectic action tie line and the eutectic composition, which is between 18.3 and 61.9% of tin. So for this alloy, the liquid begins to solidify at the liquidus temperature, producing one solid phase, which is the primary alpha phase. And solidification is completed by going through the eutectic reaction. And during this reaction, the remaining liquid phase will transform into the eutectic composition, or eutectic alpha plus eutectic beta. So that will be the second phase, which precipitates out to form this lamellae structure. Finally, let's take a look at why do we care about the composition of an alloy, because the composition of alloy will affect the properties of the alloy, especially the strength of the alloy. So here we have the plot of tensile strength versus the weight percentage of tin for the lead and tin system. So with the increased amount of tin added into lead, we know first we'll have solid solution, and then we'll have two phases, right? Precipitate, alpha phase and beta phase. So we'll have solid solution strengthened material and then dispersion strengthened material. And now the tensile strength will increase with increased amount of tin all the way up to eutectic composition. So first it's solid solution strengthening, the strength will increase, and then its dispersion strengthening. Alpha phase is strengthened by the precipitates of the beta phase, and then we have the hypoeutectic alloy, and all the way up to the eutectic composition, which has the highest tensile strength. And for hypereutectic, it starts to decrease. But if you just compare to the pure tin, right, we can say with the addition of lead into tin, the strength actually increases as well, and all the way up to the eutectic composition. We mentioned the term dispersion strengthening. Let's talk about what is dispersion strengthening. So most engineering materials are composed of more than one phases, and many of these materials are designed to provide improved strength, and this is called dispersion strengthening. So the differences between dispersion strengthening and solid solution strengthening is, in solid solution strengthening, we have only one phase. But for dispersion strengthening, we will have more than one phases. So one phase is strengthened by the addition of another phase. So this is dispersion strengthening. So in dispersion strengthened alloys, small, strong, and hard particles of one phase are introduced into weaker but ductile second phase. So in the lead and tin system, the strong, small, strong, and hard particles will be the beta phase. Okay, beta phase, and then the weaker but ductile second phase is the alpha phase. So the soft phase usually continues and present in larger amounts is called the matrix, and the hard strengthening phase is called the dispersed phase or the precipitate, like the beta phase. So a phase or a mixture of phases with a very characteristic appearance is called a microconstituent, which we mentioned before.